Welcome to the Composite Materials course. Today we'll be using energy methods, and we'll be using energy methods to derive the equilibrium equations that we already had derived using other methods. That's number one. Number two, we're going to be studying approximation theories that can be used to solve problems related to composite materials. So if we look at the strain energy density of a material, is going to be given by, for linear elastic material, is going to be given by the strain energy density, which is 1/2 the stress vector, which is a vector that contains the in-plane stresses, the 3 in-plane stresses, and the 3 shear stresses. And then you have transpose that, and then you have the strain vector, which is going to contain the strains that are in the in-plane direction, but also the shear components. And so if I look at this quantity, it's a scalar quantity when I perform this transpose like that. So it's a dot product of stress and strain. But we know that stress is related to strain through the constitutive law. So I've substituted stress by C times epsilon. C is a 6x6 matrix, and the strain in this case has been multiplied by this constitutive matrix. Recall that the constitutive matrix can be found through test data testing. We can then get the Young modulus, we can get the Poisson ratios, and the shear modulus. And when I apply a transpose to this, you have to distribute that, and when you do that, it results in this epsilon transpose C transpose epsilon. There's a 1/6, there's a 6/6, and there's a 6/1. So you get a scalar quantity, and that's your strain energy density. In classical plate theory, we made some fundamental assumptions. We assume that the out-of-plane stresses are negligible for thin laminates, meaning that the laminate is fairly thin compared to the other 2 dimensions in the in-plane direction. We also discuss the displacement assumptions are required to derive classical plate theory. And these displacement assumptions that we had basically stated that the normal to the mid-surface remains normal. We also discussed that the thickness direction is not going to change very much when you apply deformations. So those are the fundamental assumptions we made before under classical plate theory. And as a consequence, it resulted in the fact that I have these strains, and these strains are representative of the strains all throughout the thickness of the composite in the global coordinate system. And this is equal to the strains in the mid-surface of that plate. Recall that we're tracking the mid-surface behavior because the mid-surface behavior is then used to understand what is going on with the rest of the plate. Plus Z times the curvatures. So if you had no curvatures, all the strains would be simply basically acting to stretch the plate, right? But when we add these curvature terms, then we start to get some bending. The strain deflection relationships were found to be this here at the bottom, and the curvature relationships were found to be this. Now, looking very carefully, the strain deflection relationships, these strains depend on the deflections U superscript 0, V superscript 0. These are the deflections in the plane of the laminate, in the X and the Y directions. Whilst W here with superscript is a transverse deflection of the plate. So this will give me the out-of-plane deflections of that plate. And so I can now substitute the fact that U equals 1/2 sigma bold T transpose epsilon bold, and this is equal to 1/2 sigma bold transpose, but note now that epsilon superscript plus Z kappa bold, so I've made this epsilon bold, and I've used this kappa bold to be this here. And so this is now my strain energy density. I've simplified it using these assumptions. And now notice how this represents the membrane behavior with the superscript 0, okay? And then Z it represents the location through the thickness of the composite laminate. The strain energy of the plate over the whole volume, then that total strain energy over the whole volume is really the triple integral over the dV. So note that, and you have a 1/2 here. So I'm taking the strain energy density term and integrating that over the whole volume. So that's not it per unit volume, but now it's total energy. And so I'm going to now substitute for epsilon bold the fact that epsilon bold is the membrane strains plus Z times the curvatures. When I do that, I have this term plus Z times kappa bold. And then I'm going to take this volume integral and turn it into dZ dA. And the integral of that plate, if through the thickness of the plate, if the plate was thickness H, goes minus H half to H half. So very important to understand what we've done here. Very simple procedure so far, and I hope you follow it. Now, when you look at this integral here, you'll quickly realize that this epsilon bold superscript 0 does not depend on Z. You can see here that epsilon superscript 0 depends on these strains, but these strains depend only on the mid-surface deflections U, V, superscript 0. So these deflections here do not depend on Z at all. So that's this column vector, epsilon bold superscript 0. As a consequence, I can bring that outside of the integral, the minus H half to H half integral, and I'm going to now put it in this manner. So I've rearranged the term. Second step is to notice that this kappa bold also does not depend on the thickness. And so as a consequence, I can rearrange it and bring it to the outside of the integral. So it looks like this. Now notice that this kappa bold does not depend on the thickness because that's equal to these curvatures which depend on W superscript 0. And as it was discussed previously, W does not change through the thickness. So now I have arrived to this expression, but I want you to recall that we have discussed previously that we defined these stress resultants, these in-plane stress resultants, and we have found that this integral sigma bold dz is equal to the integral from minus h half to h half, where I have that stress vector sigma xx, sigma yy, and sigma xy. I don't have the remaining stresses because it's a thin plate and they're probably close to 0 for a thin plate. So we had defined these as a stress resultants, in-plane stress resultants, and these are forces per unit length. And so here in this case, you get nxx, nyy, nxy. We also have the integral of sigma bold z dc. And so this one we have defined as mxx, myy, and mxy. That's your moment resultant, and this is your stress resultant. Recall that these stress resultants are resultants acting inside the structure to react external loads. Just like stresses in 3D structures, in 3D structure, the stresses are acting inside the structure to react the external loads. These are internal loads. Think about it in that manner. And so, but we had to make the simplifications because we have simplified a 3D structure into a plate, and we only track the mid-surface. That's why these simplifications are occurring. And you may have never seen them before, except for the previous few lectures ago, which you can also find in YouTube. And so we can now take this information and kind of further expand. So this here, integral sigma bold dz, is really this n bold, this vector of stress resultants, right? So I'm going to take that integral sigma bold t transpose and make it into n bold transpose. I also have this integral sigma bold z Z dz, and this one right here is exactly M bold, and you can see that there. And so I have simplified this further into this expression now. So the strain energy density that we started with, we have now been able to take that integrator of the volume using the classical plate assumptions. I've been able to now come up with the strain energy of this plate. So I hope this is clear so far. Notice how the dA is the integral over the mid-surface now. So we're not looking at any other dA. This dA right here is a differential area element that corresponds to the mid-surface dx and dy. And note how we have kind of gotten rid of this z, but not really. Is it contained within the moment bold calculation? Now, just go back and remember the physical meaning of n and the moment m, and you can map it out to this sketch right here. Nxx is this way and has been integrated through the thickness. And then NYY goes this way and it has integrated through the thickness. In a very similar manner, we have the moments that were previously discussed. When you see S, that's really XY. So notice how we know that in 3D stresses, the stress is energetically conjugate to the strains, meaning the stress is married to these strains. And what we found for 2D plate theory, when I took this simplification from 3D to classical plate theory 2D, we find actually that the internal loads, the reacting external loads, are really conjugate. So N bold and M bold are conjugate to the mid-surface strains and the curvatures in this manner. So again, we're able to simplify the 2D plate, but we can also realize here how N bold and epsilon bold is married. M bold and kappa bold are married as well. So we can now use the constitutive law that we have previously discussed, and I don't want to go through the ABD matrix again. I invite you to go back to the YouTube lecture where we discussed where this came about, but we can use the constitutive relationships relating in-plane stress resultants and bending stress resultants to the mid-surface strains and curvatures using this formula. And here I have N bold equals A bold times epsilon bold superscript plus B bold times kappa bold. And M bold equals B bold times epsilon bold superscript plus D bold kappa. Kappa is the curvatures and epsilon superscript is the surface strains, mid-surface strains. And again, if I know the mid-surface strains and I know the curvature, I can tell you what the strains are in the global orientation system for every ply because I know the location Z through the thickness. And so that's an important consideration to not forget. And so what I'm going to do now, I'm going to use this compact form because I want to try to use matrix notation moving forward. It will make our lives easier rather than having to keep this huge matrix, which by the way was 6x6. And so, and also recall that B bold is really 0 for symmetric laminates. Another thing to consider, A is extensional stiffness matrix and D is the bending stiffness matrix. So keep that in mind also. Don't forget about what we're talking about here. M bold here is the in-plane stress resultants. M bold is the bending stress resultants. So very important to keep that in mind. Now I'm going to put this in vector notation. N bold, M bold, like that. So it's for convenience. And then epsilon superscript and kappa bold are going to be put in this manner. Now this multiplication here is equal to that. So there's nothing here very fancy we've done. We just arrange things to our advantage. Why? Because I want to be able to simplify our calculations in a way that can be convenient. And again, I'm carrying a lot of information here with very few letters. So M bold here contains the 3 stress resultants. M bold contains the 3 moment resultants for classical plate theory. And epsilon bold superscript contains the mid-surface strains, and kappa contains all the three curvatures. So again, when I multiply this through and I integrate it over the mid-surface area, I get the total strain energy stored by the system. This is nothing more than, if you think about it, is similar to the energy carried by a spring. It's 1/2 K delta squared. Very similar idea here. Now, I have now found that this is really equal to this expression here, the ABD matrix with epsilon bold and kappa bold in this column vector, in this manner, actually, in fact. So what I'm going to do, I'm going to substitute n bold and n bold by this, and when I plug it in, I have to distribute this transpose to each of them. So what I get is this gets shifted over to this side, and you get this. Now, the transpose of this symmetric matrix, it's itself, so there's nothing to do there, and then you get this expression. Now I can multiply everything out, so it looks nicely in this manner. Now, remember, this is a scalar quantity, continues to be a scalar quantity, because this is 1/6, this is 6/6, and this is 6/1. So you get a simple scalar quantity. It doesn't look like it in this here, but it is. For example, this is a 1/3, 3/3, 3/1. So that's an energy term. And this energy term has to do with extensional behavior of that mid-surface. This one here has to do with the bending energy. And this one is a coupled extension bending energy. So here I have depicted it for you. This is your membrane energy, the bending energy, and then the membrane bending energy. So very important to consider, that's the strain energy of a plate. So now let's consider the potential energy due to applied loads. The potential energy due to applied loads can be simply derived from applying tractions moving through deflections. So for example, if you were to move a block of material by a deflection delta by applying a load P, that potential energy is really P times V. Very similarly, what we've done is that we have these tractions that are acting on this body. In this case, is Q, a distributed load Q. This distributed load Q moves through these deflections W in the transverse direction, which cause this circular plate to deform. As a consequence, the potential energy is very similar to just moving a block across 3 inches, for example. If I apply 30 pounds and I move a block 3 inches, the potential energy done, or the work done, is 30 pounds times 3 inches, that multiplication. Here, Q can vary across the whole thing, so we have to multiply by the deflection, and the deflection can vary across the whole thing. So to get the real potential energy, we have to do it in this integral fashion. But in essence, the essence is still the same. It's not very different from what I just discussed. So we'll continue here looking at the principle of minimum potential energy. I know it's a new concept, but I really have to discuss it. And the idea here is, this is what the theorem really says, the principle says. It says, amongst all the displacements that can exist in the world, any admissible displacements that could occur in a structure, there is one set of deflections that will actually minimize this total potential energy. And that particular set of deflections is the one that satisfies the governing equations of elasticity. Meaning, these are the deflections, the ones that minimize the total potential energy, are those deflections that really cause the system to be in equilibrium. That's really what we're saying here. And pi is what we use as a term, and this is your total potential energy, which is made up of the strain energy plus the potential energy of the applied loads. We already found what the strain energy is, and then we also have the total potential energy. U, V, and W are the deflections we do not know. We want to find U, V, and W that in such a manner that it minimizes pi, this total potential energy. And those deflections that corresponds to the minimum value of the total potential energy, those are the ones that satisfy the governing equations of elasticity, number one, but they also corresponds to the system being in equilibrium. So it's very important to understand that, and what we mean with kinematic admissibility or admissible deflections is that, say you have a clamped beam. If you have a clamped beam, you cannot vary deflections at that clamped end because you know it's clamped. So, but if you look at deflections everywhere else and try to find those deflections that can minimize this potential energy, those deflections are really admissible because you're looking across all the deflections that could potentially minimize this potential energy. But you cannot really change the fact that the clamp condition can be, you know, removed. We're keeping that fixed, that very end fixed, okay? So this theorem can only be applied to conservative systems, meaning we cannot apply it to situations where you may have a follower force, and you can't apply it for situations where you have inelastic deformation, where you cannot recover the deformations once you apply the loads. So very important consideration that we need to keep in mind. And so let's discuss first, how do we do that? Because it doesn't seem that simple. If the strains depend on UV and W, and the kappa depends on UV and W, and N bold depends on strain through the constitutive law, and M bold depends on UV and W through the constitutive law, it's not very apparent how you can find UV and W that minimizes pi. So we're going to turn into a new concept that you may not have heard before, and the idea there is either you've heard the term line search, or we're going to use the idea of calculus of variations. So take an example of an axial bar subject to uniform load. So I'm not going to go and derive where this is coming from right now, but assume you have a total potential energy that look like this, where you have the strain energy stored in an axial bar that looks like this, and E is a modulus, A is a cross section, and then you have this deflection that is the actual deflection, and here that's a second derivative of that deflection with respect to X. So this right here corresponds to your strain energy. Now you have minus the integral 0 to L of the loading that you're applying. In this case, is a distributed load B times Wx dx. This is your total potential energy. This is the potential energy due to the applied loads. The total potential energy is pi bold, and it depends on this deflection W, as you can see. There are values of, there's a function W, perhaps, there's a function of the function W, there has to be a function W that minimizes pi, and that's the deflection, that's the function W we're trying to find. One thing I want to note, we're not plugging in a value of W. So for example, here, I'm not trying to find a single value of U, V, and W that minimize pi. Rather, I'm trying to find functions U, V, and W that minimize pi, which is a completely different question. You know, so if we were just trying to find out the value of X that minimizes a function F, all you have to take is the derivative of F respect to X and set that equal to 0. So we cannot do that here. We cannot do derivative of pi respect to W and then pretend we're going to get the minimum function, the function W that minimizes pi. It's not going to happen. This is not how you do that. You can do that if you're dealing with scalar quantities such as a function of X. So function F of X equals X squared minus 4. Well, where's the minimum occur? Well, you take the derivative of F with respect to X, and then you set that equal to 0, and then you can find the value of X. That gives you a scalar quantity. Here, I'm trying to find the function W that minimizes pi, and I cannot just do this. Why don't go ahead and pause the video and see if you can figure out how we can proceed forward. I want you to think about the questions we're really making here. I'll summarize it one more time so it's clear to you what we're trying to accomplish. There's a total potential energy of the axial bar subject to a uniform load. And so what I'm trying to figure out is what deflection W corresponds to minimizes this total potential energy. And the reason I want to do that is because it's that deflection, in fact, that solves the governing equation for this elastic bar, but it also renders the system in equilibrium. So why don't pause the video and think and brainstorm how you will approach this particular question. And so we're going to go ahead and look at how we can approach this particular question. So let's consider searching the minimum in the following way. And I know this looks very, very messy, but just follow me along and then we'll get there. We'll show you how to get it done. So if I look at this, the function W, and I'm trying to figure out what function W really minimizes pi, one possibility to explore that is to add, and say W, for example, is the one I was looking for. So I can add a plus infinitesimally small epsilon times eta x. So I'm going to have a very small value of epsilon, infinitesimal, and I don't know what that is, but an arbitrary function eta. And what I'm trying to do is figure out what function W minimizes pi, and I'm going to do it in this manner. Epsilon is an arbitrary scalar quantity. Eta is an arbitrary function that can be continuously differentiable. So this is really what we want to do now. No sweat. There's no sweat. You can just plug in W plus epsilon eta x into the expression here. That's all we did. Plug it in there. And that's why this looks like that. Epsilon does not depend on x. It's a scalar quantity. That's why it's a coefficient here. That's squared and 1/2 there. So everything looks pretty simple. This b times w, and we replace that by w plus epsilon eta. So all we've done is replace w, and anytime you see w, replace it by this whole thing. And so now I'm going to take the derivative of this whole thing with respect to epsilon, and set that to set epsilon equal to 0, and make the whole thing equal to 0. And hopefully we can find the function w that minimizes pi. And so now what I'm going to do is when I perform this derivative, you can notice here that I have a squared. So I have to do chain rule. I do this derivative, the 1/2 goes away, and I have dw dx plus epsilon, what's inside stays there, and the derivative of this respect to epsilon causes this to go away, and I only get, and the derivative of this respect to epsilon makes this epsilon go away, and so you get this coefficient here. That's what you see right here. That's what we got. And so they have minus, and then here, the derivative of this respect to epsilon, this goes away. The derivative of this respect to epsilon, this coefficient goes away. So you have eta x. So now you got this. And if I put it in a nicer format, I want you to notice how we need to evaluate this term now. Now that I took the derivative, evaluate this stuff with epsilon equals 0. And when I do that, this cancels out right here. This goes away. And so I'm left with this equation right here. And so what is this telling us? It's telling us something very peculiar. It's telling us that if I want to find the function w that minimizes pi, I better figure out a way of solving this equation here. Which is not what will have, no one here will have expected that, but that's, a theory that was based on calculus variations, and is the way to go about it. Now, what I really want to do, since eta is arbitrary, I want to get rid of this prime somehow. So what I want to do is be able to factor eta out, and I don't know how to do that. So to do that, what I want to do is integrate by parts. I'm going to teach you one way of doing that. So EAW prime is on the left-hand side, eta prime is on the right-hand side. So I'm going to break it up like that. And then what I'm going to do next, I'm going to transfer this prime to this side and then write it here at the bottom. So you can see here EAW prime x, EAW prime x. And what I've done is transfer that prime over like that. In the process of transferring prime, I've also removed the prime like that. So I have then plus, minus. I'm going to draw a sign called plus, minus. This is a way I'm teaching you how to integrate by parts, but feel free to pause the video and figure out how will you integrate by parts using a math book. If you're not able to get it, that's okay. If you did it, congratulations for being the king of integration by parts. But the idea here is I want to figure out removing this prime out of here. This is the way you do it, integration by parts. Put this prime over to the other side. And so by doing so, I've accomplished that. This bottom term will always go back into the integral in this manner. So that's why you see that here, eta times -1 times this term, that goes here. And then I have the boundary conditions. The boundary conditions from integration by parts is this term times this term. So that's the way you're going to integrate by parts if you like it. So multiply this by that, and then you get this term. So what did we find? We find that eta x is arbitrary. And I can now kind of factor that out here in this manner. So eta x can be factored. And you get this equation times eta x plus you have this boundary condition. I want to point out that for any eta x, if that needs to be arbitrary and this integral has to be 0, then the governing equation for this particular problem is this right here. Good news. The good news is that is the governing equation of a bar subject to a distributed load. Look it up in the Mechanics of Materials book. You will see that's exactly what that is. And here, this term here corresponds to the boundary conditions of the problem. And so in other words, the deflection W that minimizes the total potential energy can be determined by solving this governing equation. It's a differential equation. And you can then, by solving this, figure out, basically by solving this, this also tells you the deflections for which the system is under equilibrium when loads are applied. Let's consider another example here. So say you have I want to find the shape of this curve that minimizes the distance between 2 points. And so you know that ds equals the square root of dx squared plus this dy squared by the Pythagoras theorem. So you can see that there. If I want to find the length of this curve, I'll integrate it from 0, x equals 0 to x equals a, and I'll integrate this length ds to get the total length. And really what I want to do is, and y here is the y-axis, x is the x-axis. I'm trying to find the function y here that basically minimizes that distance. And you can see here that if I factor dx out, then I get an expression in this manner. And what we find is that what we're really doing here is we're trying to minimize L by finding y. That's not a very different problem than what I just discussed. To minimize the length L, I had to find y that makes that happen. And so very similar. So we can use the same idea of substituting for y. We're going to substitute y plus epsilon eta. And when I do that, you can see that this one right here turns into derivative of y plus epsilon eta prime. And that's squared, and that's evaluated at epsilon equals 0. I will now take this derivative of this whole thing, and when I do that, it looks complicated, but when I turn epsilon to 0 after making that derivative happen, good things do happen. It just simplifies to this expression right here, okay? I'm gonna go ahead and integrate by parts again to get rid of this eta. I'll put this whole thing on the left-hand side here, this one on the right-hand side, and I'm gonna transfer this derivative over, so you can see the ddx there, and remove the derivative from this one here. Plus minus, the bottom one goes back into the integral, while the cross term goes into the boundary condition. So integration by parts, after simplifying everything, looks very simple actually. It looks like this. And since eta is arbitrary, and we can use the fundamental lemma of calculus variations basically, for any eta, any function eta, this integrand must be equal to 0. This part here must be equal to 0. And so if you set that equal to 0 and you try to find the function y that solves this differential equation, you can do that in wolframalpha.com, Or you can do simple things. So integrate it once, you get a constant, solve for y prime, you get this, and then once you get that, you'll find that y prime is really a constant, which means that if you integrate it again, you get a line. Isn't that beautiful? Isn't that the real answer to the problem? If I have 2 points, what is the curve that minimizes this distance? And the answer is a straight line. We found that. So I want to further introduce new things that look a little more complicated, but not really. I want to make sure it's understood what we're trying to do here. So I'm going to introduce the idea of the first variation now. So I'm going to make a definition here. I'm going to call epsilon eta x, I'm going to call that del W, meaning W, we added W and a virtual deflection W, we call that, because this was arbitrary. How much this is function eta was arbitrary, epsilon was an infinitesimally small quantity that we added. So we're going to call this del W here. So in general, if I want to find the first derivative of pi with respect to epsilon and set that epsilon equal to 0, and this is equal to 0, which is to really minimize pi, really that's what we're talking about, then I'm going to call this whole thing the first version of pi. So this symbol here basically is the same thing as this whole thing. And so I want to introduce some things that will make everything easier. The first version of pi is really the derivative of pi with respect to W, del W, plus the derivative of pi with respect to W prime, del W prime, or any other derivatives you may have. This is what you will do. Del W is going to be this, epsilon eta x. And this del W prime is really epsilon eta prime x. So you can see that if I were to use this, I could even, I don't have to do this calculation I did earlier. I can actually make it much simpler. Let me give you an example. So the first variation of W squared is twice W, because W squared, the derivative of W squared with respect to W is 2W, and then you're going to put a del W next. Another example, I want to find the first variation of W squared W prime plus X W double prime. So this right here is, I had to get the derivative of this whole thing with respect to W first. And then I will have 2W, W prime, del W, right? This one doesn't have a W, so it goes away. And then I have to take the derivative of the derivative of this function with respect to W double prime. And you can see here that this goes away because there's no W double prime here. So you get plus X del W double prime, like that. I'm also missing a term here that should have been added, plus, and I have a W prime here. So the first variation of this is the derivative of this whole thing with respect to W prime. There's a W prime here, so you get the coefficient W squared. There's no W prime here, so you're left with W squared del W prime. So that's what's missing, plus W prime del W prime. So that's what's missing there. So this is a good example demonstrating, again, I want to make sure it's plus W squared del W prime squared. So that'll be the examples I've given you here. Keep in mind the first version of W is simply this extra thing we added. We took the function, we added a arbitrary function times an infinitesimally small scalar quantity. That's really what we've done. There's nothing more to it. And so I can use the approach I just discussed to keep things simple. I'll take the first version of pi, which is the derivative of this whole thing with respect to W. And you will see here quickly, there's a W prime here. So I will have the derivative of this with respect to W prime. The twice goes here, cancels out with the 1/2. You get EA W prime del W prime. You can see that there. And then there's no W prime in this term, so it doesn't contribute to it. Plus, and then I have a W term by itself. So the derivative of this whole thing with respect to W, this doesn't have a W by itself, so that doesn't contribute. This one has a w, so the derivative of this respect to w is just b, and then you have a del w. So what we really done, pause the video and try to figure it out, but all we did is to execute this formula. And now I'll integrate by parts as I discussed, plus minus, so take this del w prime, which was really epsilon eta, remember? That's what we had before. Remove the prime, put the prime over here, plus minus, and now this goes back into the integral. This cross term goes here. Since del w is arbitrary and is really equal to epsilon times eta x, and eta was arbitrary and epsilon is an arbitrary quantity that's infinitesimal, then this has to be equal to 0. And that's your governing equation for the problem, as we had discussed. So we basically showed you how to find w that minimizes pi by finding the first version of pi. Now I know this is a lot of material in today's lecture. My goal is for you to kind of understand how to minimize the total potential energy with this approach. So we're trying to find the function w that minimizes pi, and to accomplish that, we find the first version of pi, set that equal to 0, and that's nothing more than what we just did in the two examples here. Example number 1 and example number 2. I'm just doing it differently to simplify the process. As you can see, I got it really quick in one page, while before it took me a little bit longer. I could also do it here. I can take the first version of L for that line problem, the curve problem. What is a curve that minimizes the distance between 2 points? Here you have the first version of L, and you can see here that L depends on y prime, so I'll take the derivative of this whole thing with respect to y prime, and I'll have del y prime. As you can see, there's no y here, so I don't have to take the derivative of this with respect to y, because that will be 0. And so then I have this is what I will find if I took the derivative of this with respect to y prime. I get this, and then I will integrate by parts by putting this thing on the left-hand side and this del y prime on the right-hand side. When I do that, the prime gets removed and it gets moved to this side. The bottom term goes back into the integral. This cross term will be the boundary condition, which I'm not discussing right now. So for an arbitrary value of y, del y, then this must be equal to 0. And I go back and I get a line again, but I did it all in one page. And in this example, I did it all in one page, while before it took me a couple of pages to go through, as you can see here. One page for this particular problem, second page, and then now for the new example, 1 page, 2 pages, and then 3 pages. While here, we were able to do it in one shot. So what if we apply this idea of calculus variation to figure out what are the functions u, v, and w that minimize pi? So I perhaps can take the first version of pi with respect to these quantities here, and then be able to set that equal to 0, and perhaps that will take me somewhere. So I'm going to define certain things here, and I'm doing it really to simplify things. It's really done to simplify. So take this matrix here. It's a stiffness matrix that we talked about, the ABD matrix. This is the thermal total potential energy that we got earlier. And recall that this is the mid-surface strains. These are the curvatures. This is the extension stiffness, and this is your coupling term, and this is the bending stiffness. So this is what we got before. Q is the distributed load across the plate, and W is the transverse deflection. So my idea here now is put everything in an even simpler form. As you recall, this is a 1/6, but what I want to do is take that vector, that whole vector, and call it G bold for simplicity. I'm going to also take this whole thing and make it H bold. So there's a 6/6 now, and I'll put it in there just for simplicity. Same with this guy, I'll put it as G bold, and now I have simplified. It looks much simpler now. I'll take now the first version of pi, and when I do that, I will notice that G depends on deflections. So I take the first version of G transpose H bold G plus G bold transpose H del G. So that's what I got so far. I'm going to operate. I'm going to try to put a transpose here on purpose. So that will like reverse the order. So I have G transpose, H bold transpose, and this moves to the right-hand side in this manner. I also have this here. And so, and notice how H bold transpose, which is the ABD matrix, the transpose of the ABD matrix is the matrix itself because that's a symmetric matrix. So H bold transpose is just H bold. So this is what I got so far. Notice that I can now factor out del G. I can factor out del G now. And so I get G transpose times H in essence. And the 1/2 is gone now. So this got a lot simpler, as you can see. And I will now go back to what we had. We had this epsilon superscript kappa, like that. So I'm going back to what H bold was. I'm going back to this. But now there's a variation in front of epsilon superscript 0, a variation in front of kappa. And notice how there's a variation in front of W, because W needs to be varied as well. And so the first variation pi set equal to 0 got me to this point. Now I'm trying to kind of go back to what I used to have. So this multiplication here is really n bold, n bold. So this is what I got so far. And so I want you to notice that epsilon superscript 0 and kappa bold can be written in terms of the deflections. And I will be doing that now. What I want you to do now, I want you to take this epsilon superscript and kappa bold here, and I want you to put that in terms of deflections. Now the deflections are UV and W, but if you can make it U1, U2, and then make the W3 is convenient. What I want you to do is expand this. You have what epsilon superscript is, you know what kappa bold is from the very first or the first couple of slides. So what I want you to do is to realize now, so this used to be UV and W. I'm just making this U1 and U2 instead for simplicity, because I want to use index notation. And what index notation is a smart way of conducting calculations. As an example, alpha is repeated, beta is repeated. And as a consequence, think of this as a summation, double summation, alpha from 1 to 2 and beta from 1 to 2. And then this comma beta really means the derivative of u alpha respect to x beta. So now the coordinates are x1 and x2. So I want you to expand this because I think it's important to show that when you expand this, you basically get exactly what I got here when you use summation notation, or the Euler notation is what we discussed. I think it's more obvious here. You have m bold alpha beta del w comma alpha beta. And if you recall, let me go back and show you what we had. Kappa here. The kappas were w comma xx, w comma yy, w comma xy. And I'm making x and y 1 or 2. I'm making it simpler, the notation. So this right here is exactly what I have here. I want to show you that when you multiply this out, you're going to get m times del w comma alpha beta. And in reality, this gives you exactly what we had before. These are the curvatures we talked about before. So those curvatures are this kappa bold, and this right here, this coefficient here, del u alpha comma beta, that right here is this del epsilon bold superscript. So we got that right. The next step now is to get rid of this alpha and beta. So we have to integrate by parts. So we integrate by parts this term right here first. N alpha beta is on the left-hand side. Del u alpha comma beta is on the right-hand side. Beta, we only have one derivative. We pass it to this one here, and then we cross like this with this one like that. So plus minus, and here what I've done, I've included a term n. This term n is really trying to describe that there's a normal associated with the surface. You have to do that because there's a double integral. So there's a double integral area. So when you integrate by parts a double integral area, you get the perimeter. And the perimeter has to have a normal defined for the boundary condition. This term here goes back into the integral in reality. Now I'm going to, and then we didn't have that situation earlier when I looked at the single line integral, because the single line integral results in boundary terms that are just the endpoints. But here, the integral of a double integral, the integration of parts of a double integral is really the enclosed curve, and you need a normal to describe that curve. That's what this n is here, the normal. And now I'm going to integrate by parts this term right here, remove the alpha and beta. I'll remove beta first and then alpha next. And again, I will have these cross terms with the normals shown. Plus, minus, plus. So there's an error. So plus, well, there's a minus there. So that's fine, but this needs to be plus, minus, plus. And these cross terms are the boundary terms. This bottom term goes back into the integral. So this is what we get here, plus the boundary terms equals 0. And if you pay attention, you will see that for arbitrary u and deflections, in-plane deflections, because these are the in-plane mid-surface deflections, and for arbitrary value of w, the out-of-plane deflection of the plate, that the coefficient is equal to 0. So these are, in fact, if you were to expand this in index notation or Euler notation, so put a double summation there from alpha 1 to 2 and beta 1 to 2, you'll get this as the governing equations. These 3 governing equations is what you get. And this is exactly what we got in the classical plate theory lecture. So that's very, very powerful. We found exactly what we had using the total potential energy. And so in summary, and perhaps, you know, I don't pretend for you to memorize this approach, but I want you to, at the very least, understand what we did. We came up with a minimum total potential energy. We showed you that we can find the deflection fields U, V, and W, and that will minimize the total potential energy. And these U, V, and W are the ones that render the system in equilibrium. That's what we discussed. And we found that the equilibrium equations of the plate happen to be this, which is what I found in the previous lecture when I discussed classical plate theory. So as we have seen, solving this, we've already seen this, that solving partial differential equations for a plate is quite complex, and it's better to use approximation methods. And so what is the idea here? What is that we can do to approximate the solution to a problem? So the idea here is, what if I don't want to solve for the deflections in an exact way? Maybe that's too hard to do. So the idea then is to approximate W, the deflection W, for example, as an example here is, we're looking back at the axial bar problem. So forget about the plate for a second. Let's go back to the axial bar problem. If you recall that we had the energy, the total potential energy given to you as a function of W. What if we approximate the form of the deflection? So instead of finding the actual deflection, we approximate what it could look like. So this could be equal to A naught, phi naught, plus A1 times phi1 plus A2 times phi2, and so forth. These phis are known, like we're going to select them on purpose. We want to make sure that these basis functions, we call them basis functions, that these functions are known. We know what they are. We want to make sure they're complete. We want to make sure that you can differentiate them, so you can actually take derivatives, sufficient derivatives. We also want to make sure that this satisfies the kinematic boundary conditions. So if I have a clamped beam, I want to make sure that these are selected in a smart way, so I can then calculate, make sure that this deflection satisfies that particular boundary condition. The approximate function, this approximate function needs to be a complete set, like I discussed, continuous, sufficiently differentiable, and has to satisfy the boundary conditions. So for this bar problem that we looked at, which was clamped on the left-hand side, a good approximation will be A1x plus A2x squared plus blah, 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 blah. A1 and A2 are not known in this case. So what I can do, I can plug in for W, instead of trying to find a function W that minimizes pi, perhaps approximate W as a1x plus a2x squared, plug that in here, and when I plug it in here and conduct these derivatives, notice how pi became a function of a1 and a2. So it's and any other terms I may want to add. So now I don't have to find the function w anymore, because first of all, I assume the form of it, and now the function pi became a function of just a1, a2, and so forth. So all I have to do now is to find a1, a2, and so forth that minimizes pi. And that just goes back to regular calculus then. All I have to do then, and you can see here, w has been substituted there, w has been substituted here, and all I have to do now is to take the derivative of pi with respect to a1, set it to 0. That's what you will have done in calculus, normal calculus. If I want to find a1, a2 that minimizes pi, you just take these derivatives. And when you do so, what you find is a solution to the problem. For fixed bar, we can, if I had a fixed bar for the same problem, this is a good approximation. Why? At x equals x0, you can see W0, there's no deflection. At x equals L, you can see this goes away, and so W is also 0 at those ends. So it works. This is a good approximation. It's complete because x increases by 1, and the coefficients are unknown, a1, a2, and that's a mistake, a3. So this looks very well. I can find the first derivative of this whole thing, doesn't blow up. And so this is a good approximation. So what if I want to apply the Rayleigh-Ritz? And by the way, I forgot to tell you, the method we're discussing here is called the Rayleigh-Ritz method. And the purpose of today's lecture is to show you that energy methods can be used to derive the governing equations. And the second objective is to show you that I can approximate the solution to various problems using this idea, which Rayleigh-Ritz came up with, which is that instead of trying to find this function W that solves this, what if I take an approximation and plug it in? And then I can minimize pi with respect to these coefficients. That was the idea there. So I can solve for A1, A2, and A3 in that manner by doing this minimization. So 3 equations, 3 unknowns, for example, and that gives you A1, A2, and A3, which allows you to then plot the deflection if you want to plot the deflection. So what if I applied it to the plate and I considered a simpler problem? I considered symmetric laminate, so B0, makes life a little bit simpler. I wrote everything in terms of U, V, and W, because those are the ones I want to approximate and find. I've expanded here a little bit. Epsilon superscript 0, that's really this column vector. The A matrix stays the same, and the curvatures are this right here. So what I'm going to do, I'm also going to apply a distributed load to this structure. I'm going to apply a distributed load on the plate, a transverse, and also axially on the edges. So on tangentially to the surfaces, I'm sorry. So we're going to approximate the displacement field U, V, and W that satisfies the kinematic conditions, boundary conditions of the problem. I'm going to select U, V, and W to be an approximation of this kind. And I know the fees, by the way. I'll select them in a smart way so I can satisfy the boundary conditions exactly. I will then substitute these approximations back in here. And when I do that, notice how when I substitute U, V, and W for these approximations that I made here, then now everything will be in terms of CI, CI, and CI. So all these coefficients are unknown. So now I turned the total potential energy, so it's a function of just these coefficient C's. So to find those coefficients, I take the derivative of pi with respect to each of these coefficients, and I have many of them, NU plus NV plus NW, that's the total amount I have, and I will have a large number of equations and a large number of unknowns, and which I can solve using linear algebra. And once you know that, you can plug it back here, and then you will have the approximation to U, V, and W. Let's take an example of a simply supported plate. I have a simply supported plate that's under uniform transverse loading. The loading applied is P. We're going to ignore these terms because we're going to assume that D16 and D26 is fairly small. For simplification purposes, I'm going to apply a transverse load. So I'm not going to apply any in-plane loads. And if I don't apply any in-plane loads, I don't expect the mid-surface to expand or stretch or compress. As a consequence, this is the total potential energy. So just borrowing from the previous slides that we discussed, I'm going to select an approximation function of this form. And this WMN is not known. And I know this is a good, very good approximation because for a simply supported plate, the deflections has to be zero around the edges of the plate. That's really what simply supported means. And so in that scenario, you can evaluate this function for the choice of function I selected. You can evaluate it at 0, y, a, y, and so forth. And I think you're going to see very quickly that the deflection W around the plate is 0. So that's really simply supported, and it does work out. So when you substitute this into the total potential energy, it will be very messy. But when you find the first derivative of pi respect to WMN, you find this equation here. You find actually WMN. You actually find the coefficient that goes here that gives you the solution to the deflection. So this exact same deflection finding that we found in lecture 4, and why we got the same answer even though we thought we were approximating it, the solution of a simply supported plate on the distributed load. The reason we found the exact solution is because the form of the solution I selected happens to have the form of the exact solution. That's why I got the same, this answer that is the same as the exact solution. For other kinds of situations like clamp plates, you may have to select a different kind of approximation function. For other types of boundary conditions, such as clamped at one edge but simply supporting other ones, here are some approximation functions you can use. And then feel free to pause the video, but here, if you have clamped at x equals 0 and free at x equals a, simply supported at the other two edges, you can then use these approximation functions. And I can continue on, so feel free to pause the video and read through these slides. Okay, I'll proceed now. And then here, clamped at x equals 0, free at these other two edges. So again, these are the approximation functions x and y that you can select, and that will go here, right here, and right here. So the unknown coefficients are Cij's. That's the unknown coefficients. You can also study the buckling of a plate using the same idea. And so let's tackle buckling now. I have a plate subject to this shear load here of that intensity. I have this load applied to compress a plate. So these are the forces I have applied, and you can see they're acting around the perimeter of this rectangle. So gxx times u, because I have, let's see, I have gxx, and the deflection u is along this direction. So that makes sense that is the potential energy. But notice how that's at x equals a. So that's where I'm applying that. I also have a gxx times u applied at x equals 0, and that's this term right here. You also have the shear load gxy also applied, and that's going in this direction as well. So very important to consider and understand how this is put together. You also have gyy times v. You can see here that's acting in the y direction, and that makes sense that the total potential energy is the load times the deflection of that edge, and that's why there is this evaluation of y equals 0 and y equals b, because this is happening at these boundaries. I can turn these potential energies due to load applied And I'm going to do a little trick. I'm going to integrate by parts, but in reverse. So I'm going to turn this integral into double integrals by integrating by parts in reverse. I won't show you the procedure now because my purpose for the buckling part of the lecture is to demonstrate how you can approach it from the top level perspective and show you that energy approaches can be used to solve these kind of problems. So when you integrate by parts in reverse, you go from here to a double integral now, and dA is the element area at the mid-surface. You can also go from here to this one, and then now since the dAs are shared, everything comes together. The second thing we're going to think about is that when you apply in-plane loadings, we can make the assumption that the extensional mid-surface strains are zero. So assume, for example, you take a plate and you apply compression loads. If it, at the moment it buckles, most likely the mid-surface strains will be zero, okay? You'll have out-of-plane bending, but the mid-surface strains will be zero. And so what if we do that? What if we enforce that to be equal to zero? And when we do that, you will quickly notice here that, and I'm actually keeping higher order nonlinear terms, notice that, from the strain deflection relationship. So this is something you have not seen for a while, but I've made that conscious decision because to really predict buckling, you have to consider the higher order terms. And so this is exactly what I've done. Set this equal to zero, solve for u comma x superscript zero, and I do this thing here and do the same thing here. So solve for this in terms of the rest of the stuff. So once I do that, I'm going to take this information and plug it back up here. And when I do that, I get the total potential energy due to applied loads that looks like this. And the beauty of this is everything is in terms of the deflections, out of plane deflections. There's no longer anything to do with in-plane deflections. So very, very nice. And so that's great because now I'm going to take the total potential energy and use it to try to predict buckling. I can use this whole expression and predict buckling. So you could then take a solution of this form, say for a particular problem, and for simply supported or whatever you want, and plug it in here, and then minimize pi respect to each of these coefficients C. That's how you will go about that. And you'll be able to solve the problem for various types of boundary conditions. You can see that here. But what's going to happen really when you do go through this process, you're going to find that there's a trivial solution. You're going to find that either the coefficients, these coefficients we're talking about, are zero, or you're going to find this matrix right here that has to be equal to zero. And so you have to figure out when buckling occurs, and it's a little bit more complex. But if you find the determinant of this, and you set that equal to zero, you're able to find buckling when buckling occurs. Vibration, all we have to do for vibration is to add the kinetic energy of the plate, which is mass times acceleration. You can see here W comma TT is really the derivative of W respect to time twice. And so that's that term. And this is exactly the strain energy term that we had before. And now you can plug in for W. You can do separation variables. So you have W bar X comma Y times e to the I omega t. Plug this into this equation here. And notice that e I omega t can be factored out like that. So I can divide everything by e I omega t. And now everything's in a spatial domain, as you can see here. And then to find W that minimizes pi, again, I will assume a solution of this form, and the eigenfrequencies now can be found by finding the second derivative of pi with respect to each of the coefficients. That determinant here is going to give you the frequencies of the system and the natural frequencies. I want to give credit to some notes from Dr. Scott Peck and also the book from Jan Reddy. and I hope you understood the top level view. What is a top level view? Is that there's an alternate way of solving these equations, and that way for composite materials is to use the total potential energy, to try to find the total potential energy, minimize the total potential energy by finding the deflections that minimize that, and those deflections correspond to the governing equations that render the system in equilibrium. We took that to our advantage, and showed you ways that you can approximate the solution of various problems by assuming an approximation for the deflections and then minimizing the total potential energy with respect to the unknown coefficients from the approximations that we made. So this concludes today's lecture, and I hope you have a great day.